Machine vibration is a good overall indicator of a machine's operating mechanical condition. By monitoring vibration, problems such as bowed rotors, misalignment, or bearing failure can be detected and action taken before equipment failure. As a technician working with vibration measurement, you'll need to be familiar with both machine construction and probe orientation to ensure safe and reliable equipment operation. Sensor orientation is crucial to proper vibration monitoring and analysis. Improper placement or orientation could result in missing some vibration problems. There are three basic sensor mounting geometries: single position, two position, and three position. A single position monitor typically measures vibration amplitude, component displacement, or component position. Radial measurements are perpendicular to the axis of rotation. A radial-mounted proximity probe measures shaft position relative to the casing or bearing. Axial measurements are parallel to the rotational axis. An axial-mounted proximity probe can show the shaft or thrust position between shaft and casing. The axial measurement shows differential expansion between the casing and the rotor, and is especially important during a steam turbine warm-up. The shaft expands faster than the casing when the steam is applied to the shaft. The shaft could expand in length as much as 2 inches. If differential expansion is excessive, the rotor could rub against the casing, damaging the turbine. Most large machines have one end rigidly fixed and the other end able to move for expansion and contraction. An expansion monitor will provide early indication of excessive movement. A radial-mounted proximity probe may be used to measure eccentricity, which is the amount of bow or runout in a shaft. This measurement is taken at speeds of 4 to 6 RPM. Acceleration and velocity probes measure absolute or overall casing motion. The single point may provide alarms or activate a shutdown system to stop the machine before excessive vibration becomes a safety hazard. Excessive vibration can cause equipment failure, which could have catastrophic results. Many times, a single probe won't provide enough information. For example, 2 or more probes may be required to find the absolute motion of a shaft relative to a fixed point. A velocity or acceleration probe to measure casing vibration, and a proximity probe to measure shaft position. The difference between the 2 readings provides absolute shaft motion. A single sensor can only give a displacement measurement relative to its position. By positioning 2 sensors 90 degrees apart, we can get a full radial view of motion, measuring shaft vibration in both the X and Y axes. Watch this shaft spinning inside its motor. Notice the shaft position changing inside the bearing as it spins. A single sensor will only show the displacement along one axis. As long as the 2 sensors are mounted 90 degrees apart, they will show the shaft's centerline relative position. By processing these 2 signals, we can find the radial or rolling displacement inside the bearing. For a complete picture of bearing performance, all 3 measurements need to be analyzed. Critical machines may have redundant sensors installed so that a single fault or failure will not cause an unnecessary shutdown or allow a machine to continue operating with excessive vibration. Sensors must be carefully positioned, especially redundant proximity probes. Remember, a proximity probe uses an eddy current to create a magnetic field to measure shaft displacement. If 2 probes are too close together, the electromagnetic fields will interact and give each sensor erroneous readings. Proximity probes need to be spaced far enough apart so the fields cannot overlap. Make sure environmental conditions won't exceed the probe specifications. Most probes have a temperature limit. Mounting methods and surface preparation determine the range and response for the sensor. Response decreases with the amount of contact area's roughness and roundness. Velocity and acceleration sensors need to be mounted to a machine's surface to keep them from losing contact with the machine. There are several methods for mounting a sensor to a machine. A stud-mounted sensor provides the best high-frequency measurements. A stud mounting has a short, stiff stud welded or permanently threaded into the machine's surface. This method provides a relatively flat response to high frequencies. Cementing or permanently bonding the sensor to the machine's surface also provides flat response out to higher frequencies. Sensors can be temporarily mounted with sealing wax to keep contact with the machine. This method provides a flat response for medium frequencies. A magnet is a common temporary mounting method. It will also provide a flat response for medium frequency ranges. Handheld probes are the easiest sensors to use. This probe is typically used for a quick look at machine condition and for measuring lower frequency ranges. Most probes provide a reading or display that the technician can assess or interpret on the spot. These devices are often battery-powered and have an accelerometer pickup. The handheld meter is durable and easy to use. The technician can walk a pre-planned route and take vibration readings in a relatively short time. Temporary mounted sensors are subject to a variety of errors that the technician can control. Measurements taken for comparison over time need to be consistent. This means the sensor must be at the same location every time. Moving the probe even a few inches can result in very different vibration readings. One way to ensure removable sensors are reading the same location is to mark the spot with paint, weld a small flat disc, or drill a spot in the machine case. The sensor needs to be perpendicular to the machine's surface. Tilting the probe slightly could cause significant differences in vibration amplitude readings. When using a handheld probe, be sure to keep constant pressure to maintain contact on the machine's surface. Variations in contact pressure can also produce errors in amplitude readings. The sensor needs to make full contact with the machine to get the best and most accurate response. Displacement sensors measure motion by measuring the varying gap between the sensor and the sensed element. Proper mounting is important to ensure an accurate and reliable reading. Externally mounted sensors need to be supported to ensure the probe does not vibrate independent of the casing. This means rigid junction boxes and mounting adapters. If the mounting box and mounting adapter are free to move independently, the probe tip will move in relation to the shaft, even if the shaft is stationary. Because the proximity probe uses an electromagnetic field to measure the vibration, the probe must be close enough to interact within the linear range. It is critical to follow manufacturer's installation instructions. Also, there must be enough target surface for the probe to interact. Usually, the minimum target area is a multiple of the tip diameter. Attention to mounting brackets is another consideration for proximity probes. Brackets should have at least 2 fasteners to prevent the bracket from twisting. It's important that the bracket remain in proper alignment with the shaft for accurate readings. Bracket selection and sizing is important to prevent false readings during machine operation due to casing vibrations transmitted to the bracket. Brackets should have a resonant frequency at least 10 times greater than the rotational speed of the machine to prevent the probe from vibrating. Also, the shape of the bracket is significant. Longer angled brackets should not be used without a gusset. The gusset will keep the perpendicular leg from vibrating at a frequency different from the machine casing. Probes are not normally mounted below the shaft. In certain bearings, probe removal can result in oil draining from the bearing. Maintenance activities should in no way modify mounting hardware without consulting the manufacturer. In the next segment, we'll consider safety and some system maintenance. Now, take a moment to review sensor mounting and orientation in your workbook. Vibration measurement will often place you in very close proximity to exposed rotating machinery. In some cases, protective covers may be removed. Never work alone under such conditions. Be sure to have an operator who is familiar with the particular machine standing by, ready to shut the machine down. Follow your facility's safety precautions. Be sure to secure any loose clothing to keep from being pulled into the machine. At times, you may use a strobe light. This device will make any rotating machine appear to be slowly rotating or possibly stopped. This is only an illusion. In reality, the machine is rotating at its normal speed. Turn off the strobe light when it's not in use. Be careful with cables. Many times you may have temporary cables strung from your temporary sensors to an analyzer. Secure the cables to keep them from falling onto the rotating parts. Also, take care to keep cables off of floors. The cable is possibly the least expensive part of the vibration testing equipment, but it may cause the most problems due to erroneous signals. A crushed cable will cause bad signals, either with impedance problems or with stray signals. Temporary connections, such as alligator clips, may also cause false signals. These clips may act as an antenna and pick up any stray electromagnetic field. Use only manufacturer-approved equipment. Do not substitute connections and cables to connect the test equipment. Store cables to protect them from crushing, moisture, and corrosion. If you need to replace cables, make sure to use an exact replacement. Check the part number. Even though cables look the same, there are differences. An incompatible cable will cause erroneous measurements. Using exact replacement cables, you ensure that impedance and cable capacitances are compatible with your system. Some permanently installed systems will provide self-diagnostics. This can show the operator or technician that a particular channel has lost its monitoring capability. This indication may only tell you that the channel is not functioning properly. Troubleshooting will be required to properly identify the source of the problem. Consult your manufacturer's instructions for troubleshooting charts and guidelines. Calibration checks the instrument accuracy and repeatability. For vibration, a known motion, such as a shaker table or a special calibration setup, provides the input to the sensor. Measure the output and adjust if necessary. Each manufacturer will have instructions for component or system calibration. Transducer sensitivity can change with time or damage. Each transducer has a calibration constant. This constant is the same as transducer sensitivity. The sensitivity or calibration constant should be checked periodically according to local and manufacturer's requirements. Velocity probes are susceptible to sensitivity changes due to temperature and wear. As the temperature changes, oil viscosity in the velocity probe changes. Springs can lose elasticity. Accelerometers are rugged, but the crystals can crack if the sensor is dropped or if temperature limits are exceeded. Target characteristics, such as permeability and conductivity, affect proximity probe calibration. For example, a stainless steel shaft will have different permeability than a carbon steel shaft. The calibration device target material needs to be the same as the shaft material for accurate calibration. Also, the shaft surface will affect proximity probe output. Take care to keep from scoring or scratching the shaft. In most systems, the cable length between the probe and the amplifier is critical. Remember, sensor outputs are very small. Most manufacturers provide specific cable lengths with specified resistance tolerances, and these must not be changed. If the resistance is not within the tolerance level, calibration accuracy cannot be guaranteed. Cables must be secured to prevent random movement in an electromagnetic field, which will cause a false signal. Monitors provide indication for shaft vibration. These devices usually contain all the electronics needed to amplify the very low-level signal from the sensor and provide an indication. Calibrate monitors periodically to ensure that the incoming signal provides the proper output indication. Many monitor systems provide auxiliary outputs. These outputs may provide analog or digital signals for use with DCS, remote enunciators, process controllers, or recorders. In some systems, an alarm or shutdown may be a function of the monitor circuit. If this is the case, be sure to follow your facility and manufacturer's instructions to calibrate the monitor. Analog outputs are typically rated in percentage of full-scale output values. You'll need to calculate acceptable output values for your inputs. It's a good idea to take at least 3 sets of readings to ensure the output values are consistent. While conducting monitor calibration, it's a good idea to check alarm set points. Most alarms are user-adjustable, and one set should be checked periodically to ensure they provide the proper output at the proper input level. If a component needs replacement, be sure to follow your facility's guidelines for lockout-tagout, and make sure you have an exact replacement. Calibrate and check sensors before installation. Replace damaged cables. Be sure to route cables away from high-energy conductors so stray electromagnetic fields will not introduce signal errors. Ensure cables are not twisted during sensor removal and installation. Take care when closing enclosure covers to keep from pinching cables. Ground the cable in the equipment rack. This prevents signal distortion and sensing errors. Most installed monitoring systems use microprocessors to display, analyze, and store vibration data. If you need to replace a card or module, be sure to use static protection to keep from damaging replacement cards. Some systems require 2 power supplies for proper operation. Both the transducer and system monitor must have the same voltage levels. Before you replace a faulty power supply, check the voltage setting and adjust if required. After calibrating individual components, verify system integrity by inputting a known signal to the transducer with a shaker table. In the next segment, we'll look at some signal analyzers and theory. For now, review the information on safety and system maintenance in your workbook. A portable meter is a very good device to measure overall vibration amplitude. The value displayed is the total amplitude of all frequencies. A machine has multiple frequencies over a wide band from imbalance, misalignment, or equipment attached to the shaft. Each component connected to the shaft will generate its own specific frequency. To analyze vibration, we need a way to look at the signals. One tool is an oscilloscope. When an oscilloscope is connected to a sensor output, a sine wave with a period at the machine rolling frequency results. All the other components will have similar sine waves combined with the main wave. This will show up on the display screen as ripples or distortions in the overall sine wave. This can make it very difficult to find the cause for noise or vibration problems. Also, small yet significant signals can be lost in the overall sine wave. There are 2 ways to look at a complex signal. What we've just seen is the time domain. A French mathematician named Fourier discovered a mathematical technique for analyzing complex motion. He proved that any periodic function could be represented as the sum of a series of harmonic functions. Over the past several years, there have been major advances in electronics that have allowed instruments to process and plot the complex Fourier equations. The processing speed allows the output to appear as an analog signal. This process is called fast Fourier transform, or FFT. The FFT analyzer presents the signal in the frequency domain. There are several advantages for this. First, each rotating component generates a specific frequency. By plotting the amplitude versus frequency, we can correlate components to the overall vibration of the machine. something that is impossible to do on a time domain or oscilloscope plot. Secondly, surveillance measurements are easy in frequency domain. The signal is assigned a value, and over time these values can be trended. Finally, small signals lost in the time domain are detected in the frequency domain. This means that small defects can be detected while they are still small. The FFT analyzer has an input amplifier section to boost the millivolt signal from the sensor to a usable voltage for the rest of the system. Next, the signal passes through a low-pass filter called an anti-alias filter. Aliasing is a false signal caused by digital sampling of a high-frequency signal. The result is a false low-frequency component. If there are actual low-frequency signals present, the false signal will be added to the true signal, and erroneous amplitudes will result. The anti-aliasing filter removes the false low-frequency component from the high-frequency signal. Next, the sampling circuit captures a block of time from the composite signal, and the A to D converter digitizes the captured data. A typical analyzer samples thousands of voltage points per second. Now the operator can choose to see either the time domain signal, which should look like the input signal, or choose to look at the frequency domain. The window circuit prevents a leakage error if the sampled signal does not match from beginning to end. This means that the end of the sample signal must be of the same value and have the correct slope. If this automatic feature isn't present, the base will widen and not give a true representation for the signal. Aliasing and leakage are problems inherent to FFT analyzers, but they are automatically compensated for. The analyzer can expand a portion of the display spectrum. This is called zooming. Zooming is useful for improving resolution, looking at peaks relatively close to each other, and accurately measuring the frequency. Most analyzers have memory storage capability. Several graphs can be compared over time so the technician can see amplitude changes or frequency shifts. Also, data can be transferred to personal computers. There are several programs that perform analysis and show what the points mean, or track and manage vibration data. Data can be printed out when needed by several people or for permanent maintenance records. Some systems provide recorder connections directly on the monitor panel. Critical machines, machines where problems could develop rapidly, or machines whose failure could result in hazards to personnel, should have continuous monitoring. For example, a turbine typically spins at very high speeds. If a problem were to develop and the indications were to go unnoticed, a catastrophic problem could develop very quickly. A cooling tower fan usually has very large blades. If the fan threw a blade, the resulting imbalance would destroy the assembly. Continuous monitoring provides for early detection and protective action for serious vibration problems. Alarms are one protection method. An alarm may provide audible and or visual indication to operating and maintenance personnel that a piece of equipment has a vibration problem. Alarm values need to be set high enough to prevent spurious alarms. If an alarm happens with regularity, people will become complacent and not give it the attention it deserves. But the alarm needs to be set low enough so that there is time to investigate the problem before a failure happens. Another protection method is automatic shutdown. In some cases, it's prudent to shut the machine down instead of letting it continue to vibrate past a certain limit. Alarms and warnings can be established with or without delays. Sometimes vibration may be due to process problems. Operations may be able to correct the problem before machine damage occurs. Or the vibration may only be a problem if it continues over time. Many monitors provide two levels of vibration alarms. The first, or high-level alarm, warns operators of a change in vibration levels. In most cases, this level is set low enough to allow the machine to continue to operate while operators and maintenance personnel try to find the cause. A second, or high-high alarm, warns personnel of impending vibration damage if corrective actions are not immediately taken. Some systems will have more than one sensor to activate a shutdown. Logic circuits in the monitoring unit can vote whether or not to shut down the machine. The conditions necessary could be time, vibration amplitude, the number of sensors sensing a high vibration, or a combination. ISA's instrument technology training program is general in nature. When performing instrumentation maintenance in your plant, be sure to follow the specific maintenance and safety procedures provided by your facility and the equipment manufacturer.